So one of the things that I know I alluded to on Monday and that we've talked about in a couple different things are copy number detection. 'Cause that's one of the donut holes that has been missing. And so I'm going to give you an overview of where the direction that we're working on and where we're standing and some what we all think, or I feel like most of us think, are really exciting new developments. So evaluations of copy number detection using multiple platforms and sample types. Is it real? Because I don't know about any of you, but sometimes I go and I see publications and I'm like, I totally don't believe what they're saying. So just skip through. So I joined the Genome Center in February of 2012, and I can tell you that copy number detection has been on the Genome Center wish list since 2011, so basically since the day it started. And if you go look in the literature and you look at PubMed, there have been publications and claims of accurate copy number detection on whole genome sequencing going back to 2011. So it's not a new concept at all. And so I listed one of the publications there. And we had an informatics student that Sarah referenced earlier this week, and our informatics team actually implemented a detection pipeline called SCALD. We like acronyms, and I actually don't remember what it stands for at all, other than it's kind of Viking-ish, in 2014. But the truth was that even though we were running this detection pipeline on our samples, even with SCALD, to be quite frank, we were still missing copy number variant calls. And so we used to have a program where we were doing genomes in a rapidish fashion in the NICU, and we had cases that came through that we were missing. We also had seen and have seen over the past few years that external companies are offering copy number detection and deletion duplication from their samples. So for one of the cases that we were not able to find a diagnosis, so 5030, they appropriately had clinical testing ordered at the same time as research testing, because that's what we wanted. And they reported back a whole gene deletion that they detected by NGS. So that's never the place that you really want to be in. And then even going a step further, when I went back and looked at the American College of Medical Genetics abstracts for this spring, in 2018, there were well over 100 abstracts, on copy number detection. 15 were specific to molecular genomics, and they were covering panels, exomes, and genomes. And again, we see more companies that are offering del-dup clinically. And so because of this, we decided it was time to come back and do a new reanalysis. And so we've undertaken a project looking at different platforms, because of course, just like every other analysis platform or tool or library prep, there's different ways you can approach it. So for that, I'm going to touch on today are the 10x linked read system. So this system also does single cell, in case anyone recognizes that 10x name. NxClinical through Biodiscovery is a software, Dragon and GATK, and this is what Dragon Neil talked about. This is the box that's helping us do our variant calls, and GATK does the same thing, just slower. So this is kind of what it felt like. So we've been wandering in the desert for a few years trying to figure out our copy number detection. So I almost put copy number detection journey begins again, but you can see that we have multiple paths. So it's not something we've been ignoring. It's just not an easy solution. So the first one I thought I would touch on are the 10x linked reads. So they have this genomic platform, and it requires a different sample input. So for this platform, what they really want is DNA that's 100 kb in length. And so that's why when I was harping on our sample prep, that's part of it. If you want to do any different technologies, you've got to start with long DNA. And this linked read data can potentially detect copy number and rearrangements. And they have both an exome and genome workflow. Well, goodness, sorry. So what are linked reads and what does that mean? And really at the end of the day, it's a form of a synthetic long read. And so what you're going to do is that you're going to feed in your 100 kb or long pieces of DNA into the system. And it's going to take that one long piece of DNA, and it's going to mark it with a single barcode all along that piece of DNA. So they're representing it here with color. And so I think that's the easiest way to think about it, is that all your DNA is going to get a unique barcode. And along that 100 kb, you're going to mark that DNA and say barcode 1. So that we know that's what it's, all that DNA or all that sequence from that strand that links back to barcode 1, we know that it came from that same piece. And they do this by, I'll show you on the next slide, by using a process called gel bead emulsion. And then these resulting barcoded reads are called linked reads. And so what you do is that you take your high molecular weight, so that big pieces of DNA, and you put it in, you take 1 nanogram, which gives you about 300 copies of the genome, if you do the math. And they have these gel beads. And each of these beads have the barcode embedded on it. And so the idea is that a single piece of DNA is going to be picked up by one of the gel beads. And then that DNA is going to be marked with that barcode on that gel bead all along it. And so that by design, you shouldn't have 2 pieces of your DNA on a single barcode, is the idea. That won't happen. And so then this is kind of a messy slide. I know it's just from theirs, but then what happens is that you do this barcoding on their system so that you have your DNA with the barcode. And then what eventually ends up happening is that you're going to take that big piece of DNA that now has all the multiple barcodes across it, and you're going to fragment it into small pieces so that now we can put it on our Illumina sequencers or your short read sequencers. And so then you're going to go through your library prep. So same kind of idea from there on out. And you can either do a genome on that sequence, or you can go ahead and do an enrichment off of that sequence. And then when you get to the sequencers, you change your sequencing just a little bit, and that you have to sequence your nucleotides, like your genome from your patient, and then you also have to make sure you sequence that additional barcode that you put on. So you're going to have an additional barcode because you want to know what piece of DNA did that short piece come back to. And then what that allows you to do is stitch those pieces back together. So you're going to do your sequencing, and you're going to say, oh, I see this barcode. I know all of the DNA with this barcode must have come from the same strand, and it must have been on the same gel bead. So I can put all of this back together and frame it that way. And so it allows you to determine the alleles apart over that same 100 kb region, right? Because they should have only one stretch of one piece of DNA will go to one barcode, and that one barcode will be separate from the next one. So that's how you're able to do phasing. And also it's going to tell you, well, this all had to come together. So if you see a rearrangement, you'll be able to tell, because you wouldn't normally expect that DNA to be together on that same barcode. It's like kind of clear as mud. And so here, this is an example from them where it's showing that calling short deletions can be difficult, which we've already talked about. So you can't really tell from this panel, is this a heterozygous deletion and this is difficult area, or is this a homozygous deletion? And here, because we've done those linked reads and they're able to phase and say, well, this is one allele and this is the second allele, you can see here we just have low coverage in this area, and then we have a complete deletion on the second allele. It becomes clearer using these linked read technology. So we always you always have to test technology. You can't trust marketing materials. And so what we did is that we took 4 samples that we knew had deletions. So we've talked about the MMP21, and that was found with our SCALD pipeline. And then we found, we put in some other varying sizes. So this is a whole gene deletion that we talked about. And this is one that you would hopefully not be sending normally for NGS. You see this by cytogenetics. And then this is a little bit bigger gene deletion. So we knew the answer putting it in, but it actually worked. So here we can see this is for the 1p36. This is a giant deletion. That out of the 11 variant calls, or structural variant calls that the system spit out, this was one of them. And so this is a nice big deletion that's showing you the gap here. It's not the most intuitive software to look at, so that's not the important part. But we didn't see this when we ran just our regular NextGen. It was installed when we went back to look for it. So with hindsight being 2020, you could find it. So that was a success. When we look at this 45 kb deletion over this gene, the deletion was actually filtered out. But when we went back by their quality metrics, but when you went back, you could, they have a system that you can go see the things that were filtered out initially and went back kind of into that noise. You could see that that was one of 250 candidates. So that's still reasonable. 1 of 12 or 1 in 250. That's something that you can approach and find. And so when we looked at these initial 4 samples, what we found is that the known deletions were detected in 3 of the 4 samples. So that's not bad. I think that's pretty good, actually, because we didn't do anything special. We had some large known deletions that were detected, but quality filtered out. And smaller deletions were detected, but in one of the smaller ones that I didn't show you the printout, it was bucketed into one of 4,000 calls. Well, that's suddenly becoming much more difficult for us to find as analysts. Their software is called Loop, and so it has really good support for large structural variant calls if they're bigger than 30 kb. But those smaller calls, they freely admit they have a pretty big donut hole, and that one's actually really big. The other thing is that this one is missing a user interface. So I am clearly not in informatics, but it's called GUI. So it doesn't have a way for us to put a phenotype in and do a filter. So there's no Viking component to this. We talked about that. The other thing from a lab perspective is that this is a different sample preparation. So you have to know up front that you're going to do 10x, and you have to do an investment because their linked reads are not free. Those gem codes, those beads, have a cost associated with them. But if you can replace and do copy number, then maybe you're okay with that cost. It's just a weight of how the test is going to work. So I think we're closer to finding the water. I'm a beach person. So I think we're closer on our journey, but we're not quite there. So then we kept looking, and we're looking at additional evaluations. So really, if you were going to dream and pick something, you would want to implement a system that uses standard workflows as much as possible. That's just easier on the lab side and on the informatics side. One of the complications is that every single software company has the new copy number solution. So at ACMG, that was pretty much, I felt like, what every booth was this year. And so, again, the next three that we looked at was a comparative analysis of 3 copy number platforms or tools. And GATK and Dragon we already had on hand. We just hadn't been utilizing the copy number as much. And then NxClinical from Biodiscovery is a commercial solution that we have looked at. And so, again, we used a true set of samples with known deletions, and we did both exomes and genomes. So the first one that I thought I would walk us through is called NxClinical, or we usually call it Biodiscovery. So this is a software solution that can use standard or existing data, but it is dependent on the uniformity of your control. So it does need you to input a set of controls that say, here are 20 exomes, male and female, and you have to tell it, it's better if you tell it to gender if you want to tell gender on your copy number. And you want them to be prepped the same way. So you don't want to take exomes that were on one kit from 5 years ago and make that your true set for exomes that you ran today. That's not going to be a good comparison. So it needs to be the same bait set that you're using in the same prep. But it does require less controls than some of the others. So some of the other systems want you to do more controls with more data. It does have a complete analyst interface for a copy number variant that we found to be good, but I'm just going to shortcut and not really even show you this. Their variant detection and annotation is subpar. It doesn't do what Viking does for us. My box came up. Sorry. So 5030 was the known deletion of CHRNA4, and it was they were initially referred for that rapid sequencing for the neonatal onset of seizures. The research genome, as I mentioned, was negative, and again, the clinical testing came back with a whole gene deletion. And so here, when I put them together, you can see they reported back a whole gene deletion that was heterozygous and likely pathogenic. And so here's one of the screenshots that you get from the Biodiscovery or NxClinical. So here at the top, you see your karyogram that they've drawn out. And I know it's a little small, but if you put, there are 138 events with minimal filters. Which is just putting kind of their basic quality filters. So it's kind of the translation of us saying we have to see it in 5 variant reads and an allele frequency less than 1%. It's kind of the translation of that into the software system. What this allows you to do is using something that's very similar to the Saga and the phenomizer is that you can go into their system, you do it within their software, and you put in the phenotype. So you can put in neonatal seizures, and then they will generate a gene list, which very much mirrors the phenomizer. And then you can tell it how many times it has to overlap. So we said, here's our gene list using a criteria of seizures, which is pretty broad. And you only have to have one overlap. So you just have one feature that overlaps with seizures. So that's pretty broad. But once we put that in, you actually come from 138 events down to these 3 events that you need to look at for the noise filter. So 3 events is definitely manageable for us to look at. And so here, and again, we knew the answer, so that makes it a little easier on the analysis side, but it called the known deletion of CHRNA4, and this is from an exome. Up here is the BAM file, and so you can trust me it's an exome, but you can also see that we have this large area where there's no coverage. And so we're comparing it to standard exomes. At the top, it's telling you the gene, and then here, it's telling you all the people that this has been called in. So one of them is the exome, one of them is the genome, and one of them is the parent's father. And for anybody who's done array before, this is where it's generating it generates synthetic probes, is how I like to think of it. And so here at 0 would be copy number neutral, so that you have 2. So if you had a gain, you would see those jump up. There would be higher. And it's calling a deletion a heterozygous loss, so we see their coverage drop down to 1. So one of the things that we thought was interesting is that the whole gene deletion of the CHRNA4 was reported clinically, and we knew that, and that certainly was a good explanation for the seizures that the child had and that the father turned out it also had. But you can see that the deletion actually stretches into the next gene, which is collagen COL2A1. And so all of the samples again are calling the deletion well into the next gene as well. And so it does give you pretty good resolution. This is even with an exome that we were seeing. So that was good, right? First one in, positive. So we had another case. This is one of our earlier cases that they were again enrolled in the rapid genome protocol, and the diagnosis was actually made by array before the genome was even started. So I clearly remember the gen counselor calling me, and that's because we don't have to consent people for clinical testing, so the team can just add it. So there was sometimes a lag time between that. We also have a good array team. And so I remember the counselor calling me saying, have you started your testing? Because we clearly have a diagnosis. And so we didn't even run the genome, to be honest. At that time, the testing was canceled. And so we did run an exome on this as a test because we knew we had a family in our research protocol that had a known big deletion. And so can anyone see the deletion on this? Exactly. So this patient had 4P. They had Wolff Hirschhorn. So this isn't even looking at any variant filters. This isn't even opening up that next page. This is just at the front. And right here, this red bar right here is that they have a known syndrome and a pretty large deletion. So even that is, we thought, pretty exciting. These yellow, just to orientate you, these little lollipops is what they look like, are single nucleotide variants that they're calling. And then anytime you see yellow, this is where they're calling an area of homozygosity or loss of heterozygosity. So again, we have encouraging results. This is a female that we ran with developmental regression. And so we can see lots of little, these carrots or arrows are little deletions. But you couldn't see it obvious, so they didn't have a giant cytogenetic deletion or change. But with one phenotype filter of developmental regression, which again is pretty broad, and only one match that was required, we have only 3 copy number variants that we needed for interpretation. And these are off of exomes, not genomes. And the answer was an MECP2 deletion of exons 3 and 4. So it will give you all of the transcripts up above, and these are the exons. It doesn't mark you as clearly, so you have to either go into Viking or you have to be able to go find which transcript you want to look at in order to find what the deletion is. So I tried to put the green arrow here so you could see that there's a deletion called over these 2 exons. Here's where it's marking the deletion, and then here's where it's showing you that p-value where it dropped off. So these are off of exomes, which is great, but our genome's better because we all know that they are, especially if you're going to look at copy number because you don't have drops in coverage, right? So it's kind of a rhetorical question. So really it should have been how much better are genomes? And so we've been able to run comparative genomes and exomes, and of course you get a much higher breakpoint resolution with genomes as we expected. But it's always nice when things behave like we want them to. And so sample 4 that we've put in was a male with muscular dystrophy, and again he had a known deletion of exons 47 through 50 in DMD. And when we put the exome in, it was actually initially missed. And then we realized that we needed to go work on our settings. So there is a lot of back and forth in making sure that you have the right controls and that you have your right settings put to that. And there's a fair amount of work that's gone into optimizing that. And the deletion was called right away in the genome. And of course, a hemizygous deletion is a little bit easier. But here, what I'm showing you again is I'm zoomed in over the exons 47 through 50. And here we're calling the homozygous copy, they call it again homozygous on the top, and the exome, or in the genome, and this is the exome, and you can see the drop. So what's nice is that within your data set, it will tell you how often it's been seen. So you can say, well, that's just a common change that everybody has, or that's noise in our system. We knew these were the same people. But here, if we load the genome and look at that, you can see how crisp and clear. Again, it's hemizygous, so I made it easy, but it very clearly calls. That's the deletion matches the BAM coverage. So it's very clearly genomes are giving us a much better resolution of where our actual breakpoints are. Not everything is perfect, and we don't catch everything, so I don't want to give this false impression that it's working all the time. So we do have a misdetection, and this one is over list 1. You can kind of see the drop in coverage right here a little bit, but it also just kind of has low coverage. And we've loaded this sample multiple times and tweaked everything that I can think of tweaking, and we're still missing this one. The deletion is just too small. So we loaded the genome, and here you can kind of see where the deletion is. So it's there, and it kind of drops down, but it's not reaching significance. So they're doing a read depth, and then they do behind the scenes, what they're doing is looking at read depth across your controls and how different is your read depth in your sample. And this one isn't meeting the significance. And if you make it loose enough that you get the significance, you introduce enough noise that it's now really difficult to find. So it's not perfect. Well, so now we've had 2 pretty good success stories. So the first one worked, we're just kind of missing a component for interface, and we have to do a separate step. And then the second one is working pretty well, but that's a software that we have to purchase. It's an additional one. So we also wanted to look at how other platforms were performing. And so we did, Neil and Byung-gil and his team did a comparison of what are the compute times and what does it take for us to do this. So if you just recall, Dragon is very fast, and it's still very fast even if you're running copy number. The GATK is slow, but it takes quite a bit longer. And then the biodiscovery is in the middle, which is what we would have predicted. This is just to give you an idea of the kind of numbers of deletions that are being called across them. So the minimum size from 20 ranging up to 309. And then the maximum size that's being called between them. So it actually, they're not as different as they look. So they're all performing pretty similarly. The same with duplication. So we see variances, but they're not that different. So then we look to see how many deletions and duplications are being called in each sample over our cohort by each platform. And so we go from 146 in biodiscovery to 110 in GATK to 27 in Dragon. And in duplications, we're ranging anywhere from 10 to 61. So again, they're all kind of in the same general area. I think the difficult thing is that we can feed samples in, and we know they might have a pathogenic deletion, but they have other deletions and duplications, and there's not a good true set that we can say, oh, you should definitely have, you know, our sensitivity is 98% or our specificity. So that's one of the difficult things that Neil's been working on. But here, one of the things, even if you don't read, so these are the samples that we put in. We wanted to do a true positive. By that, we just mean we know these samples have a deletion or a duplication. And how is each one performing? And so what I think is really interesting when you start to come, so the ones that are in red are ones that were missed. And if you look across each deletion and duplication or each finding, there's no one platform that really missed every single one. With the exception, this plod one, oh, no, we caught the plod one in this platform. It's just the wrong color, sorry. Which I think is really interesting. So if we put in a known set of deletions and duplications across these 3 platforms, no single variant is being missed by all of them. And so they're approaching it in the same manner, but they're doing it differently. So that let us, maybe one of the things we need to think about is if you're going to do copy number, do you need to try to find a way to integrate to different platforms? And I can remember a time in sequencing when people were trying to do 2 different sequencing methods to try to validate their variants that they were seeing. So here's some other considerations and comparisons just when you're thinking about them and looking at them to sum it up. So the NxClinical-Biodiscovery has a really nice user interface, but it doesn't have an automated text report that can be spit out, so there's a little bit of manual moving up and down. We have to put some effort in to automate the loading, and the numerical copies aren't reported. So it'll say high copy number gain, and you can look at that value and how far it goes from 0, and you can infer whether it's 3 or 4 copies, but it's not assigning that number. It's putting that back on you. Dragon doesn't have the same analysis user interface, so that's going to have to be designed. It's fast, but the zygosity is not reported. And then for GATK, there's not a user interface, but that is cheaper. And the zygosity not reported. They do, both Dragon and GATK, though, do have an automated text format that you can use downstream, so that's nice. All right, so I've just showed you that you can take software and you can put in things that you know are there, and you can find them again. I'm not sure that's that exciting, although it was for us. But can we solve strikeouts? So CMH37 was clinically diagnosed with Mowat-Wilson disease. So this patient clinically met the phenotype of the syndrome. But clinical testing of ZEB2, which is the gene associated with that, was negative. And they'd had chromosome, they had microarray, and they had sequencing. So they were enrolled in our exome sequencing project in September of 2011. And maybe the thought was maybe there's a novel gene. So there's a second gene that's causing this syndrome, because clinically they clearly have it. Except for it was negative. There was no sequence variants were identified. And then the genome was negative. And then we thought, well, we don't have enough coverage, so we'll run a new exome because we have a new kit that we're using, and that was still negative. So this case was added to our continued strikeout list. And so I think I've said that a few times, but that's just the way we describe something. If we can't find a diagnosis after we've looked at them, we say we've struck out, and we keep them on a list of cases to come back to. And so we've been revisiting some of the strikeouts now that we have this copy number project. We ran a 10x linked read genome, and we loaded the new exome and genome into NxClinical software. And this is what we found when we opened up NxClinical. So here, instead of a deletion, what you can see is that there's this increase in coverage, and this happens to be an increase in coverage in ZEB2. And with the phenotype filter set to an overlap again of only 1, so we're being pretty generous with that. There were only 10 copy number calls to evaluate. Although I'm going to be honest, when it came up with 10 and then I saw ZEB2, I didn't focus too much on the other 9. They will give you some information about what they're calling. So it's calling it, this is their bucket or their kind of equivalent of our ACMG buckets where they're calling it likely pathogenic. They will go ahead and give you the cytoband, the chromosome location, the length that they're calling it, which is not as accurate if you're doing an exome, right? Because you have drops in coverage. So it'll say, we think it's this, and it's the best we can do because here we pick up coverage again. So it's not going to give you the same resolution as a genome. And then it tells you information about the syndrome if you're not familiar with it. So that's kind of nice to have. But we already run the 10x too, so I went back and looked at 10x. And so when we pull this up, what this is doing on their site is that these are the reads they are able to phase, and then these are reads that weren't phased. But here you can see on this allele that there's this increase in coverage. So this landed in their donut hole that is way smaller than 30 megabases, but they did find it. It just wasn't being called out in their system. So now we have 2 methods that are showing a duplication. And so this is being sent for confirmation because all of these are in a research protocol. This one, here you're looking at the genome. Right. We put an exome in as well, and it's in the exome as well. But you don't see the nice, you don't get the exact breakpoints. Oh, so this software is, the filtering in the software is what we were able to find. And the calling algorithms have gotten better. So duplications are harder than deletions. So I think it's a combination of better calling algorithms. This one would have been run before Scald. I'm not sure it's ever even put through Scald. I didn't ever go back and look, to be honest. But then the other combination was the ability to do the filtering based on phenotype, so that there were 10 to look at instead of thousands. Correct. Right. 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 And in 10x, the reason, like, I just went and typed the gene in because it's too small. It was in their bucket of unbinned, or misassigned, so they don't feel like it has a good enough confidence for them to call it out on their front page. But you can go in and type in any region that you want to, and since I'd already seen it on the biodiscovery software, we just typed it into 10x and then came up, and then you can see, oh yeah, they're seeing an increase in coverage there as well. The one other thing that I just thought I would touch on is that it does call, as I showed you, the absence of heterozygosity. So this was a case sent from an astute clinician that they saw a homozygous missense variant in a gene called ARSA that was detected. And they actually suspected that there was a stretch of or loss of heterozygosity or area of homozygosity. And that was just based on a manual inspection of IGV because that was homozygous. But they didn't see it, and they didn't have parents. So they just were clicking through IGV to see, well, how many are all of the SNPs, as Carol mentioned, in this area, all the changes homozygous? And as best you could tell for a ways they were, but that's clearly not scientific. So as a test, we just loaded it into the system, and sure enough, the software is giving us an estimation of an area of homozygosity of about 16.5%. So you can see this person has very large regions that it's calling as AOH. Now this isn't validated. We have not, the system is totally on the research protocol. So how accurate that 16% is and how accurate these bins are, I'm not sure. This is often an exome, but it definitely fits with what the analyst had seen. So we thought that was interesting, and this is a component that the software will give you as well without doing anything extra. So I just kind of wanted to give you a glance about where things are, where we're seeing with copy number detection. So it is rapidly improving and changing. Again, no deletion or duplication was missed by all the platforms, which I think is really encouraging, because that's where we were not that long ago with single nucleotide variants, and now no one really questions those anymore. And is there a possibility you need to use, would two systems make your calling even more robust? And I think right now, as an analyst, so not as an informatician, but as an analyst, the biggest piece that sets things apart is that analyst interface that lets you do the filtering. So I think we're getting closer. We're almost there. And these, I just wanted to mention all the people some of the people that have been working closely on the copy number, with Bjorn Gill doing a bunch who just joined us today. And then our analysis team that you've met. And if you have any questions, I will try to answer them before I hand it over to Jeff. Right. Right. So we have, well, they'll give you a file. They'll give you a variant file to look at. And so with Scald, what we would get is this long Excel file. And so then you would kind of have to go through and see. And so if those, those might be the better calling solutions in the end. But then we have to really lean on Neil's team for help. No, that would be the dream goal. When I clone Neil, that'll be.
That would be because detection is actually separate from looking at it, right? So we're trying to build in support to actually review calls into Viking. That would be something similar, and then for us that would be a good solution. And also the bit that's not so important to Emily is the lack of an actual VCF file, standard file format. For the computational folks, that's really important. Yeah, you can't actually interact with things that are over here.
The Dragon or GATK?
It gives you a VCF file, so positional based. We'll say there's a duplication or a deletion from here, this rough general area.
So, good. It was exons 2 and 3. How many megabase? 22,387. 22 KB. Yeah. From the genome. I also like being able to like visualize, like I like the BAM. For me, the BAM under their synthetic probes that they've made, it visually it works well for me. It doesn't work well for everyone though. So if anyone wants to see it, I do have it on my laptop, so I'd be happy to show people in close because I know it's kind of tiny, blurry on the screen, but I'd be happy to show anyone. So they're they don't go by license, they go by samples. Okay, so next up is Jeff. Sure. You don't have to. So a lot of these samples that we dumped in were old. We did run some new ones, like for the wolfish horn, the 4P. We just had never run it, but it was a sample that I knew we could use as a control. The 37, I didn't rerun anything because we already had run everything multiple times in an attempt to find it. So we just took the old. Oh, that's 10x. Sorry, that was 10x. No, that's fine. It is confusing.